Good. Okay, we're going to cover a very important concept in chemistry called the mole. It's used all the time, and it sometimes gives students trouble, but it's really just a number. The mole is just a particular number, kind of like a dozen. When you hear dozen, you know that immediately I'm talking about 12 of something. The mole is a similar type of thing. The mole is sort of the chemist's dozen. And it's equal to, so 1 mole of something, like 1 dozen donuts is 12 donuts. If you could have 1 mole of donuts, you'd have a heck of a lot of donuts. 1 mole is 6.02 times 10 to the power of 23. It's an enormous number. And we'll be using this number quite a bit. The reason why we use this is because this concept helps chemists to count. And we actually count in chemistry by weighing. That may sound a little bit funny, but if you can imagine like this piece of chalk, this chalk has some calcium in it. And if we were actually to try to count every single calcium ion that's in this piece of chalk, it'd take forever. It'd take longer than our lives to actually do that. But there's this awesome trick that we can do, that we can actually count things by weighing them, and the mole fits into this idea because it works like this. If you'll look at the periodic table, which you can actually see on slide number 10 of the PowerPoint, you're going to see a symbol of an element, such as hydrogen, the very first element. And let's see, I think it's up near the top. They have the atomic number. And then down below, 1.008, it says. 1.008. We talked about this number down here before. This is the atomic weight. There happens to be a relationship between the atomic weight of a particular element like hydrogen and 1 mole of that element. Very convenient. And it works like this. For hydrogen, if you have 1.008 grams of hydrogen, you've got 1 mole of hydrogen atoms. Very, very convenient way of being able to count by measuring. And so I'll just write this here, that the atomic weight of an element in grams contains 1 mole, or that's the same thing as 6.02 times 10 to the 23, that very large number of atoms. So it's really slick. So if you just look at your periodic table, what I want you to do is I want you to say, why don't you tell me how many grams of helium are in 1 mole of helium atoms. So just look across at the periodic table at helium, and if I look at, let's see, helium on the periodic table, down below, so I see the helium with the 4 up here, and if I look down below, I see 4.003. And that tells me that if I have 4.003 grams of helium atoms, I know exactly how many moles of helium atoms I have, which is 1 mole of helium atoms. And that tells me that I have 6.02 times 10 to the 23rd helium atoms. You can do that for any element on the chart. So like gold, its symbol is Au. Its atomic number is 79. And if we look at gold's atomic weight, it's 196.967 grams. So if I have 196.967 grams of gold, I know I have 6.02 times 10 to the 23rd gold atoms. So there's a couple problems on slide 9, I believe it's slide 9 of the PowerPoint, that I'd like to go through just to give you a feel for some of the problems that you might do related to the mole. And the first problem asks, what mass of lead, symbol capital P little b, is equal to 2.50 moles of lead? Let's run through that problem together. So the first problem asks, if I have 2.50 moles of lead, we want to know what's the mass of that. So how many grams of lead is that? That's our question. So I'll just set this problem up like I normally do. I take the information I know, 2.50 moles of lead. I set it over 1 to remind me that I'm going to do a conversion factor here. And what I want to do is I want to convert moles of lead. So I'm going to put that on the denominator because this is the unit I want to get rid of. And what do I want to convert it to? I want to convert it to grams of lead. And this connection, grams of lead for every mole of lead, that's the atomic weight of lead. So we need to be looking at the periodic table. So that's what I'll do. I'm going to look here at the periodic table for lead, element number 82, and down below its symbol I see 207.2. 207.2. And that 207.2, what that tells me is this many grams of lead is 1 mole of lead. I just want to pause and point that out for a second. When you have the periodic table, you have 118, that's how many elements there are, you have 118 different conversion factors with the atomic weight. For every single element, we've got an atomic weight. Now I can write this type of equation for every single element in the periodic table. So this is my conversion factor that's going to help me convert grams of lead into moles of lead, or like I want to do here, moles of lead into grams of lead. This is a skill you're going to have to know how to use to be fluent in chemistry. But in this case, we see that I want to convert moles of lead into grams of lead. The 1 goes with the mole, so I'm going to place that here. And the 207.2 grams, that goes up here with this unit here. So this tells me what to do. I'm going to take 2.5 moles of lead, I'm going to divide by 1 mole of lead, and these units cancel. And so to find out how many grams of lead are in 2.50 moles of lead, I just take 2.5 and multiply by 207.2. Let's find out what that is. 2.5 times 207.2, 518 grams of lead. And there we have it. Let's do the next problem. What amount of tin is in moles is equivalent to 36.5 grams of tin? So in this case, instead of going from moles to grams, the question's going in the opposite direction. We have a certain number of grams of tin. We want to know how many moles that is. So let's set that problem up. $36.5 grams of tin, and I want to know how many moles of tin that is. Oh, it looks like I was setting up my problem already here, so let's set it up here. 36.5 grams of tin. I'm going to place that over 1. And I'm going to need to multiply this by a conversion factor to convert my grams of tin into moles of tin. If I'm going to do that, what should go on the denominator and what should go on the numerator? Think about that a bit. Try to write it down. Let's see. I want to get rid of grams of tin. And I want to go to moles of tin. This is the step that I want to do. So these will cancel, and I'll convert my grams of tin to moles of tin. Where should I look to find how grams of tin and moles of tin relate to one another? Periodic table, of course. So we're going to look at element number 50 on the periodic table, which certainly is tin. I'm seeing 118.771 on the bottom. So I see tin. Did I say 771? Was that right? No, 711. It's atomic number 50. This tells me that for every 118.711 grams of tin, I have a mole of tin. This tells me my grams per mole. So let's see. I'm going to place the 118.71. That goes with my 711. That goes with my grams of tin. That's a mole of tin. So in this case, when I do the multiplication, the grams of tin will cancel the grams of tin. And I'll end up with moles of tin as my unit. I'm going to take 36.5, but this number's on the denominator now, so I'm going to take this and divide by this to find out my moles of tin. Let's figure that out. 36.5 divided by 118.711. I'm getting 0.307. That would be moles of tin. That's that particular problem. Let's have you try the middle problem. Why don't you just pause the video, we'll try that middle problem, and then I'll work it through with you. A graduated cylinder contains 32 centimeters cubed of mercury. They give you the density of mercury, so there's going to be some extra steps in this one. This is a little more complicated than what we've been doing. But the density of mercury is 13.53 grams per centimeter cubed. How many moles of mercury are in the graduated cylinder that contains 32 centimeters cubed of mercury? Give it a shot. All right, let's work this out. I've got 32.0 centimeters cubed of mercury. They're giving you a volume of mercury. That's the same as 32. I hope you see that's the same as 32 milliliters of mercury. Mercury is a liquid. And we want to know how many moles of mercury are in the cylinder. So there's a couple steps in this one. So what we're going to have to do is we're going to have to take this volume and convert it to mass using the density. And then once we convert to mass, you can always go from mass to moles. We can do that using the periodic table. So let's try it. So I have 32 centimeters cubed of mercury. And I want to convert the centimeters cubed of mercury into grams of mercury. Grams per centimeter cubed, that's the density, right? The relationship between grams and volume, mass and volume, that's just the density. And they give you the density here, 13.53 grams per centimeter cubed. So I'm going to put the 13.53 grams with, the 13.53 goes with the gram, and that's for every centimeter cubed. So at this case, if I just did this, I'd convert my centimeters cubed of mercury to grams of mercury. Now to convert to moles, we're going to know how we're going to do that. We're going to look at the atomic weight on the periodic table for mercury. I'm just going to set up the units here. Let's see, it looks like I want to get rid of this gram of mercury, so I'm going to put that on the denominator. And I want to convert that to moles of mercury, so that's going to go in the numerator. And I'm going to look up mercury on the periodic table. That's element number 80. 200.502. So if I look at mercury on the periodic table, element number 80. Down here below, that's the atomic weight of mercury. That tells me that for every 200.5 roughly grams of mercury, I'm going to have a mole of mercury. All right, so let's take this and plug it in the right spot here. 200.502 grams of mercury That's a mole of mercury. Let's see if my units have worked out. In this step, the centimeter cubed or a milliliter of mercury cancels this centimeter cubed or milliliter of mercury. In the second step, I convert this gram of mercury, cancels numerator and denominator, into a mole of mercury. So ignoring the ones, because multiplication by 1 and division by 1, that's the same number. But in this case, I see I'm going to take 32. I'm going to multiply by 13.53. And I'm going to divide whatever that is by 200.502. Let's see what that comes out to. 32 times 13.53. Divide that by 200.502. 2.16. And so we've done the conversion that allows us to see that 32 milliliters of mercury has 2.16 moles of mercury atoms in it. Well, this one's tough. We'll do the next problem. What is the average mass of an atom of sodium? That's an interesting question. What's the average mass of a single atom of sodium? How in the world do I figure that out? So this is what they've given us. What they've given us here, okay, let me write the problem down. What is the average mass What's the average mass of an atom of sodium? What's tricky about this problem is you have to both figure out what it is numerically that is given to you in the problem that kind of seems hidden. And then you have to figure out where you're going. And then you got to figure out how to get there. So there's a lot of steps here. But just think about it. What numerical value have they given you in this problem? They want to know the average mass of a single atom of sodium. So what they've given you quantitatively here is 1 atom of sodium. So I can write this. 1 sodium atom. They've given you an actual number of sodium atoms. How much of a dozen is 1 sodium atom? Well, it's 1/12. How many moles of sodium atom is this? Well, it's 1 out of 6.02 times 10 to the 23rd. It's a very, very tiny amount, but nevertheless, it's a quantitative number that we can use. Now, we want to go from this number to, what do we want? We want the mass. That's what we want. We want to know how much does 1 atom weigh on average. So let's see. How am I going to get from number all the way to mass? Well, what you want to recognize is that you can first go from number to moles. I can do that in this following way. I know, it doesn't matter what I'm talking about, but I know that 6.02 times 10 to the 23rd of anything, sodium atoms, marshmallows, if you could have that many marshmallows, but nevertheless, this many sodium atoms is 1 mole of sodium atoms. Everybody agree with that? That should make sense, yeah? This is the definition of a mole. Just like 12 is a dozen, 6.02 times 10 to the 23rd, that's a mole. Now, why am I converting to a mole? Because mole helps us to connect to grams, and that's really ultimately where we want to go. That's where we want to head. So how do I find how a mole of sodium atoms connects to grams? Periodic table, the molar mass, the atomic weight. I might say molar mass, I might say atomic weight. I use those synonymously. Listen to what I'm actually saying when I say molar mass. What's the mass of a mole of something? So we sometimes use the words atomic weight when we're talking about that number on the bottom of the symbol on the periodic table. Sometimes I'll use the term molar mass. What's the mass of a mole? What's the grams per mole? That's the connector that connects grams and moles. So I'm going to look at sodium on the periodic table. And I'm going to see that it says, oh, it's a little tough to see. Let's see if I can blow this up a little bit. Yep. Down beneath sodium, element number 11, it says 22.990. So let's see. 22.990. What's that tell me? Ah, that's right. That's how many grams of sodium is equal to 1 mole of sodium. That's what that bottom number is always going to connect. That bottom number will always tell us the grams in a single mole. And I'm going to use this conversion factor to give me to the next step. Because I want to get rid of moles of sodium, and I want to move to grams of sodium. And there I've done it. Let's see, I've got my sodium atom, cancels these sodium atoms. I've got a mole of sodium atoms, that's going to cancel this mole of sodium atoms. And hey, I've done it. I've converted my single sodium atom into a certain number of grams. And I will take my calculator and I'll do this calculation. Now this particular calculation, it's going to require you to know how to put scientific notation in your calculator. If you don't know how to do that, you might want to send me an email or get online and figure out how to do that on your own. But we definitely have to make sure that you know how to use your calculator to answer these particular problems. That's part of the process of being able to do chemical calculations. Now for me, if I take my cell phone and turn it sideways, then a bunch of new functions show up, and one of them will allow me to do this type of exponentiation where I can do numbers times 10 to the 23rd. And I'll sort of describe what I'm doing here in my cell phone as I do the calculations. Hopefully in some way you'll be able to make sense of that. Actually, maybe if I just come up to the camera, let's do that. So you can kind of see what I'm doing on the cell phone. Your calculator may very well be different. Okay? So I'm going to go to the first fraction, which is 1 sodium atom. I'm going to type 1. That's my number of sodium atoms. I'm going to go to the next fraction. We multiply by 1, of course, but I don't need to do that because 1 time, well, I'll just do it. 1 times 1, that's still 1. But now I'm going to divide by 6.02 times 10 to the 23. Watch how I do this. 6.02. See this EE? I'm going to press that, and in my head when I press it, I'm going to think times 10 to the power of. Now I'm going to hit 23. And I'm going to hit equal. So now that step, what I just did there is I divided by 6.02 times 10 to the 23rd. Now we see I'm going to do the next fraction, and that tells me I need to multiply by 22.99. So that's pretty easy, times 22.99. And there's my answer, 3.82 times 10 to the negative 23 grams. That's pretty tiny. Does that make sense? Let's think about that. Let me just write the answer here. Equals 3.82 times 10 to the negative 23 grams. That's a really small number, but it's not 0. Does that make sense? Well, we're trying to find the average mass of a single atom of sodium. How heavy do you think a single atom is? It's not very heavy, right? I mean, these things are stinking small. Atoms are very, very small. So if we can kind of imagine what a mass of 3 times 10 to the negative 20, 3.8 times 10 to the negative 23 is, that's pretty small. So of course, this result in some sense makes sense. All right, let's do that last problem. This one's going to be a little different here. This problem asks you to see how many atoms of oxygen are in 10.0 grams of, oh, that's a compound now. We're not just dealing with a single element, we're dealing with a compound. We're dealing with sodium nitrate. I have to figure out how many atoms of oxygen are in a compound that's not pure oxygen. How am I going to do this? Well, let's start with what we're given. And what I'm given is 10 grams of this thing. Okay, so I've got 10.0 grams of sodium nitrate. Wouldn't it be nice if we could figure out how many grams of sodium nitrate were in 1 mole of sodium nitrate? And then if we did that, look what we can do here. What you should recognize is that if I have 1 mole of sodium nitrate, that's a compound, and each unit of sodium nitrate has a single sodium, it has a single nitrogen, and it has 3 oxygens. That's what that O3 down there on the bottom means. So it's like if I have a mole of cars, how many moles of tires do I have? I got 4, right? Because for every car, there's going to be 4 tires. So if I have a mole of cars, I have 4 moles of tires. In a similar way, if I have a mole of sodium nitrate, I have 3 moles of oxygen atoms. So I can already write that here. 1 mole of sodium nitrate is going to be 3 moles of oxygen atoms. So really, the only new thing that we need to figure out here is how many grams of sodium nitrate are in 1 mole of sodium nitrate. And I hope it makes sense that this is really kind of easy, because what I have to do is I just have to figure out how many grams are in a mole of sodium. I can do that. We just did that in the last problem, right? That's 22.99. We saw that in the last problem. How many grams are in a mole of nitrogen? And I just happen to remember some of these. That's not going to be exact, but it's really close to 14.0. And oxygen's the same way. I just happen to have that one memorized. It's 16.0. It's very close to that. These numbers won't be exactly what you see when you look on the periodic table, but you can go back and do those exactly if you like. For this problem, it's going to make them 14 and 16. And notice, because I have 3 oxygens, I had better multiply this by 3. And if I add these up, well, I'll have the molar mass of sodium nitrate. I'll have my grams of sodium nitrate for every mole of sodium nitrate. So let's write this out. Let's just do it. So I'm going to have my sodium here. I always do it kind of this way. I got my nitrogen, and then I have my 3 oxygens. So let's see, my sodium's 22.99. My nitrogen is 14. And my oxygen, there's 3 of them. That's going to be 16 times 3, which is 48. So I just add those up. 22.99 plus 14 plus 3 times 16 plus 48. 84.99. What is that? What is that 84.99? That 84.99 tells me how many grams of this full thing are in a mole of this full thing. So I'm going to write that in here. 84.99 grams of sodium nitrate for every 1 mole of sodium nitrate. And I think I've done it. I'm going to go back and just check. I want to know how many atoms of oxygen. Atoms. I need one more step. Are in 10 grams of sodium nitrate. If you look at where the calculation is right now, I've converted grams of sodium nitrate to moles of sodium nitrate. We're going to actually push this all the way to the number of oxygen atoms. At this point, while a mole is a number, I want to actually explicitly get the actual number. I don't want to just stop here at moles. So there's one more step I need to do. Oh boy, this is going to be a little, it's going to be a little crowded. But the next step is going to be for every 1 mole of anything, 1 mole of oxygen, I've got 6.02 times 10 to the 23 oxygen atoms. So I'll write this out a little more clearly. Let's just do it one more time. I'll erase it and do it. Let me make sure it was what, 84.99. Let me just do it one more time so you can see the whole thing.
You can go about as far as that plug in the wall under the chalkboard to your left.
Okay, great. Thank you. Yep. So I've got 10 grams of sodium nitrate, and we did a calculation, and in that calculation we were able to show that for sodium nitrate, 84.99 grams of sodium nitrate is 1 mole of sodium nitrate. And here's a new trick, but it's a good one for you to know. When you see a compound, and I see this subscript 3 down here, that tells me that for every mole of the full compound, there's going to be 3 moles of oxygen atoms. Now, I could have done this step. We want to know sodium, what this step would look like. It would say 1 mole of sodium, 1 mole of sodium nitrate would have 1 mole of sodium. Just like for every mole of cars, there's 1 mole of steering wheels. But in this case, it's more like tricycles. For every mole of tricycles, we have 3 moles of wheels. And because, I mean, technically, if you're asking for how many, you could stop at moles, because just like 12 dozen, that tells you how many. We could technically stop here, but I actually thought it'd be good to go ahead and push it all the way to the actual numerical number of oxygen atoms. So we can write here 1 mole of oxygen atoms is 6.02 times 10 to the 23rd oxygen atoms. And I'll pull my calculator up here and I'll take you through this calculation so you can see it. I'll turn the calculator sideways and all those functions pop up, and I'm going to do the calculation from left to right. We're starting with 10 grams of sodium nitrate. We'll need to divide that by 84.99 grams of sodium nitrate for every mole. Curses. Let's try that again.
Sure.
10 grams of sodium nitrate divided by 84.99 grams of sodium nitrate for every mole of sodium nitrate. So at this point, I know I have basically 0.12 moles of sodium nitrate. But for every mole of sodium nitrate, we have 3 moles of oxygen. So let's multiply that by 3. So I know that in 10 grams of sodium nitrate, I have about 0.35 moles of oxygen. But we want to know how many numbers of oxygen atoms we have, so I'm going to multiply this number by 6.02 times 10 to the power of 23. That's a lot of oxygen atoms. 2.12 times 10 to the 23rd oxygen atoms would be our answer. And just to give you a little, to sort of close, we've done all the problems on this slide. Just to sort of close this idea of the mole, I want you to think about this with me. So a mole, if I take I want to make sure I have this right. I think it's a ½ teaspoon. Hey Siri, what's the volume of a tablespoon?
A tablespoon is a large spoon used for serving.
Hold on.
In many.
Hey Siri, a tablespoon has how many milliliters?
1 tablespoon is 14.79 milliliters.
Is that right? I thought it was 30. Interesting. Okay. So I just want to give you a little context on this idea of a mole and how it relates to the sizes of atoms. So I want you to imagine a tablespoon of water. It's not a lot of water. It's like a swallow. It's like a soup spoonful. So in a tablespoon of water, there's about 1 mole of water molecules. That's it. 1 mole of water molecules in a tablespoon. Now, what I want you to imagine is we're going to take every single water molecule in that tablespoon and we're going to blow it up to the size of a sand grain. All right? So if I take that spoonful of water, which has a mole of water in it, roughly speaking, and we take every water molecule in that spoonful and we blow it up to the size of a sand grain, how big of a container am I going to need to contain all those sand grains? I think maybe a swimming pool, or a building, or something a little larger? What do you think? How big would the container need to be? Well, in order to contain a mole of sand grains, just little grains you see at the beach, what you're going to need to do is you're going to need to build a wall around the state of Texas, 50 feet tall, and then you can contain all those sand grains. A mole is a huge number because atoms are extremely tiny. And in order to talk about atoms, we need really big numbers because they're so small that an enormous number of them can fit into something as small as a tablespoon. All right, that's it.